everybody. In this video, I'm going to go over section 3.4, the definition of the derivative. So I'll go over the definition, I'll do some examples, and then we'll talk about differentiability, and I'll do some more examples. So here's a definition of the derivative of f at a. This is just the instantaneous rate of change, right? This is just the instantaneous rate of change of my function f at a. Okay, so now that we're going to define this as the derivative, we need some notation. And then notation will be, I'm going to erase this, and then notation will be f, a little like apostrophe, and then of a, okay? And this we're going to read as f prime of x, okay? So from now on, whenever I say f prime of x, I'm talking about the derivative of a function f at a, which is the same as the instantaneous rate of change, okay? So then I know that f prime of a, okay, is now the derivative of f at a is the instantaneous rate of change of my function f at a. It's the slope of the line tangent to the graph of f at a. Perfect. Now, if I want to write the definition of the derivative as a function of f, I literally take my definition here, okay? And then instead of getting a number at the end, after computing that limit, I'm going to get a function that depends on x. So I'm going to get a function of x. So I'm going to erase this, and this, and this, and then I will replace a's with x. So now this is f prime of x, which represents the derivative of my function f as a function of x. So let me give you other notations, okay? Notation. F prime of x, that is Lagrange's notation. Leibniz notation is df dx. This is probably my favorite notation because it tells you that, it tells you that f is changing with respect to x. It looks like a slope, right? Perfect. You can also say dxf, meaning you're taking the derivative of your function f with respect to x. And then, of course, if y is equal to f, then you can say that this is dy dx equal to dx, y, etc. Okay? So let's do an example. We want to find the derivative of f of x equal to root of x, okay? So what we're going to do is you have to start by writing the definition down. So f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. But we know that that means that we have to replace x plus h. So here we go, root of x plus h, the whole thing inside the square root, minus root of x all over h. Now, if you let h go to 0 now, then h goes to 0, so you would get root of x minus root of x, right? And this is equal to 0 over 0, right? So what that tells me is that when I'm computing the derivative, I'm going to get a 0 over 0 form, and this requires more work. But this is why we went over how to compute limits. We know the techniques, and if we have the square root like this, if we have a square root, we have to use the conjugate. We have to multiply and divide by the conjugate, which is exactly the same roots, but instead of subtracting, we have to add. So let's do it. So what I'm saying is that this is just equal to the limit as h go to 0 of root of x plus h minus root of x all over h, and I will multiply by the conjugate, okay? And I know that the conjugate is root of x plus h plus root of x, but if I multiply by it, I have to divide by it. So root of x plus h plus root of x, okay? Now, I'm going to simplify this, and this is the limit as h goes to 0, and I know that the whole point of multiplying by the conjugate is to get rid of the square roots, okay? So what do I get? If I do root of x plus h times root of x plus h, I get root of x plus h squared. So I get x plus h, right? Then I do root of x plus h times root of x minus the same thing, so that goes away. And then I have minus root of x times positive root of x, so I get root of x squared, minus root of x squared. So I end up with minus x all over. And then just by looking at this, I know what's going to happen, right? I know what's going to happen. x minus x, and then this h will cancel this h. So do not multiply the denominators together. Just write it down like that. You see what I'm saying? Like, do not write h times root of x plus h times root of x, because you want to cancel h. So I'm just going to write it as h times root of x plus h plus root of x. Okay? So now, when I do that, as I said before, I know that I'm going to be able to cancel this h with this h. So I will end up having the limit as h go to 0. Again, keep lim until you compute the limit. I get 1 on top divided by root of x plus h plus root of x. Okay? Perfect. Now I know that h goes to 0, so h goes to 0, and I'm left with 1 over root of x plus root of x equal to 1 over 2 root of x. Okay? So think of what we're saying here. What we're saying is that the derivative of my function, it's equal to 1 over 2 root of x, meaning as long as you can substitute, as long as it is in the domain of the derivative, you can plug anything in, okay? You can plug in anything, okay? So, beautiful. At all times, keep in mind that the derivative represents the slope of the line tangent to the graph at a point. So in this case in particular, knowing that f prime of x is equal to 1 over 2 root of x, I can compute the derivative of 2, 5, 10, 11, whatever I want to, as long as it is in the domain of the function, okay? Why am I saying this? Because I need it now. Now I want to find the equation of the line tangent to the graph of the same function at x equals 4, okay? Now, you know that if you're computing the equation of a tangent line, you need two things. Actually, not only, if you want to compute the equation of any line, you need two things. So in order, I'm just going to write it down. In order to compute the equation of a line, we need, what do we need? 1, a point. 2, the slope of the line, right? So I can either give you the point and the slope, and then you can write the equation, or I can give you 2 points. But this is the equation of a very, very, very important line, which is a tangent line, okay? And we know that by definition, the derivative represents the slope of the line tangent to the graph at a point, okay? So here, we already know what x is, so we know that x is equal to 4. So step 1, let's find the point. Well, the fact that x is equal to 4 tells me that y is equal to f evaluated at 4, which is root of 4, so we get 2. So my point is, the point is 4, 2. Perfect. Now I need the slope, okay? But it's the slope of the tangent line. Slope of the tangent line. So the slope of the tangent line is just the derivative evaluated. So slope is the slope of the tangent line. And the slope of the tangent line, by definition, is the derivative of the function evaluated at x. Equals 4 in this case, okay? Equals 4 in this case. So slope of the tangent line is equal to f prime of 4. Well, we know what f prime of x is. F prime of x is equal to 1 over 2 root of x. So if I want f prime of 4, then I just have to do 1 over 2 times root of 4, okay? So this is just 1 over 2 root of 4, and this is equal to 1 over 2 times 2. We get 1 over 4. So the slope of the tangent line, it's equal to 1 over 4. So what I'm saying is that, let me just draw it real quick here. We know that the graph of f of x equal root of x looks something like that. So if we have 4 right here, if this is 4, then this is the equation of the tangent line. This is the tangent line. That's the tangent line. So that tells me that this is 2, And that tells me that the slope of this line is equal to 1 over 4. Makes sense. At least we got something positive. Now we have to compute the equation of the tangent line, okay? So that tells me that equation of line tangent to root of x at x equals 4 is, I'm going to say y minus y1 equals m times x minus x1, okay? You know the formula. So now this is the slope. That slope, which is slope of tangent line, which is 1 over 4, right? It's right here. And then the point is 4, 2. So, of course, if I'm going to use the same variables, then this is my x1, y1. So 4, 2. So let's do it. So now this is 4, this is 2. So we get y minus 2 is equal to 1 over 4 times x minus 4. Okay, so this is y minus 2. I'm going to distribute that 1 over 4. So I get 1 over 4. I get 1 over 4 times x, which is just 1 over 4 times x. And then I have 1 over 4 times negative 4, which is negative 1. So negative 1, okay? And then I'm almost done. I'm going to add that 2. So I get 1 over 4x minus 1 plus 2. And minus 1 plus 2, that gives you 1. So this is the equation of my tangent line, meaning the equation of this line. That's the line tangent to the graph of root of x at x equals 4. One more time, this is the graph of root of x. Okay? Perfect. All right, so computing the derivative involves computing a limit, okay? So if the derivative of a function exists at a, that means that that limit exists. You were able to compute that limit, and we say that the function is differentiable, okay? The function is differentiable at a. If you try to compute that limit and you can't for some reason, then we say that the derivative does not exist, and we say that the function is not differentiable at a, okay? So there are only 3 cases where the derivative does not exist, okay? Meaning there are only 3 cases where a function is not differentiable at a specific point. So let's see. Okay, so here I have the 3 cases. I'm going to look at this one first, okay? I'm going to look at this one first because it looks very similar to the graph of root of x, which we already did, okay? So if you go back to the graph of root of x, right, which looks like that one, and we go back a little bit more, we know that the derivative as a function of x is equal to 1 over 2 root of x. Can you think of a value of x that if you plug into the derivative, it's undefined? Yeah, the answer is 0, okay? So in this case in particular, the domain of root of x is from 0, right? All real numbers greater than or equal to 0, but the derivative is not defined at 0. So that tells me that here, if I were to draw the tangent line, I would get something that looks like this, which is a vertical tangent line, right? This is the case, like, for example, if you get that you have to divide by 0, like 1 over 2 root of x, okay? So in this case, we say that the function is not differentiable because you have a vertical tangent line, okay? Here, if you were to compute that limit, this function is not continuous, okay? This function is not continuous, okay? So if it's not continuous, it cannot be differentiable. I think the best way of explaining this is by literally taking the definition of the derivative. The derivative represents the slope of the line tangent to the graph at a point. So if the function is not continuous, then there's no point. How are you going to be tangent to something that does not exist? How are you going to touch the graph at a point that it's not part of the graph? So in order for a function to be differentiable, it has to at least be continuous, okay? It has to at least be continuous. So here we're going to say that, in this case, it is not differentiable. It is not differentiable. I'm going to say A here not differentiable because it's not continuous. So not differentiable at A because it is not continuous. Okay? And then the last case here we have, this is A. Okay? So as I said before, in order for a function to be differentiable at A, it has to at least be continuous. But that's not enough, right? This function is very continuous at A, okay? But if you compute if you were to compute the derivative, right? There are different ways of looking at this. But for example, this is, say the slope of this line is equal to 1, then the slope of this line, it's -1. So when you take the one-sided limits, you don't get the same thing, okay? Right? That's like if you were to compute the derivative using the definition, and I'm going to do it in a couple of minutes, if you were to use the definition of the derivative. But also, if you use your intuition a little bit, one more time, if you have a corner, how are you going to put a tangent line? It's going to, yeah, right, it's going to fall. There's no way, okay? So it has to be very smooth so that you can have tangent lines, okay? Perfect. So let me just write this down real quick. So these are the cases where derivative does not exist, meaning the function is not differentiable, where derivative does not exist. Okay? So hopefully you're looking at this and you feel like you've seen something like this before. That looks very similar to the graph of absolute value of x, okay? Even though the absolute value of x is continuous at x equals 0, it's not differentiable, okay? I'm going to do this by using a definition of the derivative at A that is equivalent to what we did before, okay? I'm doing it on purpose so that you get exposed to both definitions. So another way of defining the derivative at A, so another way of defining f prime of A is limit as x goes to A of f of x minus f of A all over x minus A, okay? So now this is the derivative that I want to compute, okay? But before I do it, I have to go back and think of what the definition of the absolute value is. And I know that the absolute value of x is equal to, well, the opposite of x if x happens to be negative, and then x if x is greater than or equal to 0, okay? So since I'm computing the derivative at x equals 0, then we know that this a will be 0 in this case, okay? So let's do it, right? Now we have f prime of 0, it's equal to the limit as x goes to 0 of f of x minus f of 0 all over x minus 0, okay? I've replaced my a's with zeros, okay? Perfect. So what do I get then? Then I get that this is equal to the limit as x goes to 0 of the absolute value of x minus the absolute value of 0 over x minus 0. But I also know that the absolute value of 0 is equal to 0. So this is just the limit as x goes to 0 of the absolute value of x divided by x. And this is where the magic happens, okay? I know that the definition of the absolute value depends on whether x is less than 0 or greater than 0, okay? And I'm computing the limit as x goes to 0. So I'm going to have to take the one-sided limits, okay? You ready? We need to take the one-sided limits. If we get the same thing, then that's the limit. If we don't get the same thing, then that limit does not exist, and I'm going to tell you that's what's going to happen. Let's do it. Okay, so let's see. I'm going to take the limit as x goes to 0 from the right of the absolute value of x over x. I'm going to take the limit as x goes to 0 from the left of the absolute value of x over x, right? So go back to the definition. If I'm using this definition for x less than 0, then this is what happens when I approach 0 from the left. And this is what happens when I approach 0 from the right. So I get to replace my absolute value with the definition, right? Since I'm taking the one-sided limit. So what do I get here? I get that this is just the limit as x goes to 0 from the right of x divided by x equal to the limit as x approaches 0 from the right of 1, I get 1. Perfect. Perfect. Now, limit as x approaches 0 from the left, I get negative x divided by x. And now I get that this is just the limit as x approaches 0 from the left of negative 1. And the answer now is negative 1. Right? Well, since you got negative 1 from the left and positive 1 from the right, then at 0, that limit does not exist. Okay? Does that make sense? So I'm just going to say, let me just move this a little so I can write everything on the same place. So what we're saying is that now, therefore, 3 dots, therefore, limit as x approaches 0, right, of f of x minus f of 0 over x minus 0, aka f prime of 0, does not exist. Okay? Perfect. So this is how you prove that absolute value of x is not differentiable at x equals 0. Okay? Let's do another example. So here I have my function that says determine x values where f is not differentiable. Okay? So now we know. Now we know that the function has to be continuous, right? The function cannot have vertical tangent lines, and the function cannot have any corners. So, in other words, if there's a vertical tangent line, if there's a corner, if the function is not continuous, those places, at those places, the function is not differentiable. Okay. Long story short, corner, not differentiable. Discontinuous, not differentiable. So, function, so f is not differentiable at x equals 2 because of sharp corner, and x equals, what is this, 4 because discontinuous. Okay? Perfect. Now, suppose the following graph represents position of an object in time, okay? A, determining intervals where velocity is positive. So we know, right? We know that the velocity represents change in position with respect to time, right? So that tells me that in calculus 1, that tells me that velocity will be the derivative of position, okay? Meaning the slope of a tangent line, okay? So for example, if I draw my tangent lines here, right, I'm getting that s prime of t is greater than 0. Then here at 3, I get a horizontal tangent line, so I know that here s prime of, actually I can say s prime of 3 is equal to 0. Then after 3, if I draw my tangent lines after 3, I get something negative. Oh, that's awful. I get something negative, right? I get negative tangent lines, right? Negative tangent lines. Then at 5, I get again horizontal tangent line, so I know that s prime of 5 is equal to 0, and so on. After 5, we get positive slopes, okay? After 5, we get positive slopes. So if we want to, t is greater than 0. So if we want to do part A, we say determine intervals where velocity is positive. We know that velocity, I would say velocity is the derivative of position, and we know that it is positive from 0 to 3, and then from 5 to infinity, okay? Or whatever, 5 on, okay? So I'm going to say, let me just, so that we don't get too confused, I'm going to change this instead of a little arrow there. I'm going to say 8, whatever, who cares, okay? So then it is positive, I'm going to say it is positive from 0 to 3, right? Because we have positive tangent lines, and the tangent line represents the derivative, which is the slope of the tangent line, which is the change in position with respect to time, and I'm going to say 5 to 8, okay? Now the second one, part B, we have to determine intervals where velocity is 0. So we know that we don't actually have intervals, we actually have just places, right? At t equals 3, we have a horizontal tangent line, meaning 0 derivative, meaning 0 velocity, because velocity is a derivative of position. And then at 5, so we say t equals 3 and 5. And you can even say, because of horizontal tangent line, because horizontal tangent line. Okay, perfect. That's it. That's all I have for section, whatever the section is. That's all I have for derivatives. I'll see you next time.